I like the example at the very beginning of this section because it's actually a pretty common application of this law of cosines thing. So I'm going to reproduce it here. What if you're on a boat and you're traveling, going from south to north, and then the captain makes a 20-degree turn and continues? If in the first part of the trip you manage to go 10 miles, and the second part of the trip you manage to go 8 miles, remember that the angle turn that you made was 20 degrees. The question is, how far are you now from where you started? The triangle we have here, I'm going to blow it up a little bit, looks something like this. Now, remember that we were going north, due north, and we turned 20 degrees. So 20 degrees there, but that means that this angle here is the balance of 180 degrees. So this angle here is 160 degrees. And I'm going to erase the 20-degree angle. It's just going to confuse things. It's important information, but it's how we got this information. So I'll leave it on this diagram, but we're going to call this one 160 degrees. The other things we know about this triangle are that this side has a length of 10 and this side has a length of 8. We can do angle-side angle problems using the law of sines, but this is a side angle side problem. So for this, we need something different. And I'd like to show you where this new rule we're going to be using comes from. Your textbook shows it. I don't know how easy it is to understand, so I'm going to kind of try to talk through that explanation a little bit. Let's say we're on, actually I'm going to go down here a little bit. Let's say we're on the unit circle. And let's draw myself a circle here. That's not too bad. I'm going to grab a random point. We know the coordinates of this point are the cosine of, maybe I should name my angle here. Let's call it theta. Cosine theta, comma, sine theta. And that is in part because this is the x coordinate and this is the y coordinate of that point. And on the unit circle, this has a radius of 1. This hypotenuse here is a 1, right? That's a radius of my unit circle. Now, if I were to take that and stretch it so that, for example, my radius, let me use a different color here. My radius is some unknown r, then my x-coordinate is going to be, I'm going to call this r, I'll call this x prime because it's a different x than the other one. And I'll extend my y-axis. The y-coordinate is going to be, I'll call that y prime. They're going to get stretched as well. So where my original x-coordinate was only here, my new x-coordinate is out here. My old y-coordinate only went to there. My old y-coordinate only got to there. My new y-coordinate is way up here. Now, if I do what I've been doing with these, I'll start with this one because I didn't actually put it in the diagram. I drop a horizontal or drop a vertical line down there, then I end up with a right triangle. And I can do that with this big triangle as well. There's my new x-coordinate, right? In fact, let me go ahead and just draw that in as a solid line. So now what I have here is a small right triangle, but I'm interested in this larger right triangle. I want to know what the coordinates of this point are. So let's go ahead and figure out what the sine and cosine, I'll start with cosine. What is the cosine of this angle here? Well, looking at the small right triangle, I have adjacent, which is x, over hypotenuse, which is 1. And that's how I got, let's see, let me write that down. X over 1, that's the cosine of theta. And the sine of theta, again, just looking at the small triangle, is opposite over hypotenuse. So opposite is the y, right? The length of this side of this triangle, that's the same as the y coordinate. So that's going to be y over 1. The hypotenuse is 1. Looking at the larger triangle, the cosine of theta is the side adjacent, which is x prime. And that's just, I'm just using x prime here so that, because I want to make sure that we understand this is not the same value as x. I could call this x1 and this x2 or something like that, but I just called it x prime. Same thing with the y's. The cosine of theta is equal to the length of the side adjacent, which is my x prime, over the length of the hypotenuse. But the length of the hypotenuse is the hypotenuse of this large triangle, which is r. So it's x over r. And I'm now going to solve for x prime, I'm now going to have to multiply both sides of this by r. So I get x prime equals r cosine theta. And in the interest of time, I'll point to it, but I won't write it out. The sine of theta is opposite over hypotenuse. Sine of theta is opposite, that's y prime, over hypotenuse, which is r. And if I multiply both sides by r, I get r sine theta for my y value, my y prime value. So the coordinates of this point are r cosine theta, r sine theta. If the radius happens to be 1, the r's are 1, and so it's just cosine sine. But if the radius is anything else, then you have r cosine theta, r sine theta. So for circles bigger than 1 or smaller than 1, or the radius bigger or smaller than 1, you need sort of this generalized version. So now that we have that understanding, I'm going to erase my work for this sort of new version of the coordinates of a point on a circle, or the coordinates of a point in a plane, frankly. And I'm going to erase most of this, but I'm going to leave that there, and I'm going to draw a different diagram. Here's a set of axes, x and y. And I'm going to draw a triangle on this set of axes. I'm going to have a point, one vertex of my triangle here. I'm going to have another vertex of my triangle here. So there's one side. And then I'm going to have a third vertex way out here. Now, in theory, I should be able to do this with any triangle I like, but because this is going to demonstrate where a formula comes from, I'm going to use this specific layout. Again, this is just from your textbook. This is the most common sort of derivation of this formula that I've ever seen, so we'll just go with this. Drop a vertical line. That means that this is a right angle. And then we're going to label the vertices of our triangle A, B, and C, which means our sides are A, B, and C. And we're going to call this value x. Remember that C has coordinates. This is the point on a circle, right? Not a unit circle necessarily, but a circle nonetheless. And it's going to have coordinates r cosine theta, r sine theta. So kind of keep that in mind. I don't want that there just now, but keep that in mind. And this coordinate right here is x. We're just calling that x. We're giving it that name, which means that the length of this side here is c, but the length of the side, the length of that line segment, the length of this line segment right here, I'm going to do that in yellow, oops, is x minus c. The whole thing is x. This part of it is c. So this part of it is the whole thing minus that part, x minus c. All right, now I want you to take a look at this triangle. That's a right triangle. So the squares of the lengths of the two sides, the two legs, is equal to the square of the hypotenuse. So we can write a squared equals y squared plus the length of this side, which is x minus c. So x minus c, that length, squared. But we have a different way of writing x and y. If we think about c as having coordinates x, comma, y, we can think of that as r sine theta, sorry, r cosine theta, comma, r sine theta. Except, what is my r? It's b in this case. So I'm going to have b cosine theta, comma, b sine theta. And remember that while these are the coordinates of this point, we get those coordinates because this point is out x units and up y units, right? So I have x labeled but not y on my diagram. Well, that means that I can rewrite this equation, which is just a Pythagorean statement of the Pythagorean theorem. The length of the hypotenuse squared is equal to the sum of the lengths of the legs squared. A squared equals y squared, but y can be written as b sine theta. So I have to square that, plus x minus c, and x can be written as b cosine theta, but I still have to have my minus c, and then square that. Now I'm going to expand this. Remember that ab squared is just equal to a squared b squared. Well, here's my a, and here is my b, so that's how I get that term. And here I have to use the binomial theorem, or at least make sure I remember to multiply this out as a minus b all squared, which is a minus b times a minus b, which is a squared minus 2a plus b squared. This is not equal to a squared minus b squared. Be careful. Please be careful. Okay, so I'm going to apply that here. There's my a squared minus 2ab plus b squared. That's from here. Now I'm going to make the observation that both this term and this term have a b squared in them. So I'm going to factor that out. And lo and behold, I have a sine squared plus cosine squared, which is 1. Now I need a little more room, so I'm just going to move some things around just a little bit. This might take me a second. Bear with me. And then I can rewrite this as a squared equals b squared times 1, because sine squared plus cosine squared equals 1, plus c squared, just reordering my terms, right? I have a b squared plus a c squared, I'm just putting that next, minus 2bc times the cosine of theta. And this is what we call the law of cosines. That's another good formula to have on a note card. Now, before we can apply this, we need to make a couple of observations. Look at where a, b, and c are in the formula. A is what the whole thing is equal to. There are no other a's over here. B and C appear both here and here. Make sure you do the order of operations correctly when you're doing these computations. The only angle we're interested in here, the only angle that comes up is the angle theta. So before we can apply this formula, we need to know what theta is, where it is, and how it relates to the other parts of the formula. We can't just randomly choose sides A, B, and C and some angle in the triangle theta. We have to use the angles that this formula came about from a specific relationship, right? So let's go find A, B, C, and theta. Theta was actually the angle that we named, that we were working with when we said that the sine of theta was y over r. And theta was the angle that had a cosine of x over r. So notice that angle theta here is actually also called angle A. I think going forward it may actually be easier to use A instead of theta, so I'm going to change theta in my formula here to A. I'll just do that off screen. I'll be back in a minute. So I've replaced all my thetas with A's. And one of the reasons I did this is that I think it makes it really a lot more clear what the relationship is between A squared, the side you're looking for here, and the angle A. Notice that the left-hand side only has the side length A in it, nothing else. The right-hand side does not have the side length A in it at all. It does have the angle A in it, and only once. So side A and angle A are related in this way. Side A is this length right here. Angle A is angle theta. It's this angle right here. They're opposite each other. Using that convention that the side length opposite the angle should have, those two things should have the same letter, but the side length is going to have a lowercase and the angle is going to have an uppercase letter. So using that convention, these are opposite each other. This is the side length opposite angle A. Now, what the other two letters are, b squared, or b and c, b squared, c squared, and b and c up here as well. They are the other two sides, but notice that they are the sides that enclose angle A. Let's get rid of that theta too. It's a little confusing now. So what I have here is an angle A inside between B and C. It's the included angle, right? So A and angle A, B and C enclose angle A. And that's the relationship here. To use this formula on our original scenario, I can erase this scratch work as well. To use this formula, I need to know what sides and angles I know and what sides and angles are missing. I only have one angle, and so I'm going to have to use that here. So I might label this A. That makes this side A. And that's actually the distance I was looking for, so that makes this a formula completely appropriate. Let's go ahead and plug it in. I have A squared, the thing I'm looking for, equals B squared, that's going to be 8 squared, plus C squared, that's going to be 10 squared, minus 2 times B times C times, the wrong tool, times the cosine of A, and A is 160 degrees. Oh, I barely made that on the screen. Now, again, some of this I can do by hand, and I'm going to go ahead and do that this time because I want to be really, really clear to point out that there's a common error a lot of students make here, and that is to do this arithmetic, and somehow this cosine of A over here gets left off, and the inclination is to say, let's see, that's 160. The inclination is to do this arithmetic, but you can't because we have to do our order of operations in the right order, right? What I have here, let me go ahead and write my cosine of 160. Everything is correct so far, but what often happens is students want to do this arithmetic, right? But this is a subtraction sign, and this is implied, but it's multiplication. And you have to do order of operations, is you have to do multiplication before you can do any addition and subtraction. So what I can do is say that this is 164 minus 160 times the cosine of 160. But I do not want to subtract 160 from 164. I do not want to do that. It's so easy. It's only 4. It makes it so nice, but it's wrong. So don't do it, right? What I need to do now is go figure out what the cosine of 160 degrees is. My calculator tells me it is negative 0.939692. So I can go 69, and that's correctly rounded to 5 places. And that's a negative number. Leaving the whole 15 decimal places in my calculator screen, I'm going to hit the times button and then 160, and I get negative 150.35 something. So now I have 164 minus, because I just did this, cover this minus up, right? Let's cover it up. And I just did the negative 0.9 times 160. I did times positive 160. So this is still a minus sign. So I have minus 150.350819, so 35082. Now we just copied this negative down here, so I cover that up and say 160 times negative 0.9, that's a positive times a negative, which is a negative. That gives me this negative times a negative, which is a positive. So I'm going to change this sign, and when I do this arithmetic, 314.350819, so 35082. Now we have to be careful here because it feels like we finished the problem, but what we have found is a squared. So a is therefore equal to the square root of that value, which is about 17.72994 and the next digit is a 1, so I don't need to worry about rounding. And that is my answer. This is the distance between where we started and where we ended up, having gone 10 miles, turned through 20 degrees, and gone another 8 miles. Now, one thing to make sure we point out here is that we went 10 miles. This is a linear distance. And then we went another 8 miles, which is another linear distance. And the distance between those 2 points is also, therefore, in miles. So now we know how to solve a side angle side problem. Recognizing that it's side angle side tells us that it's a law of cosines problem. This is the law of cosines. I have a couple of things to point out. One is that it doesn't have to be doesn't have to be my angle. I had a triangle that was just generic. It hadn't been labeled at all. And so I had written down this version of the law of cosines because I had that and I knew that the only angle I knew was this angle right here. I just went ahead and labeled it A. But sometimes the triangles are already labeled or labels are given to you in the problem. So it's worth knowing that another form of this formula is b squared equals a squared plus c squared minus 2ac times the cosine of b. And here, little b is only in this position, and capital B is only in this position in the formula. The other two letters, a and c, are here and here. In the same way that a was only here, and lowercase b and c, the other two letters, b and c, were only here and here. The third version of the formula is c squared equals a squared plus b squared minus 2ab, the cosine of c. The angle c is in play, then it's little c that we have out here on the left. The other two letters are a and b, and those are here and here. So I don't think you need all three versions. You're welcome to write all three versions of this down, but really this is the only one you need, and then you can just follow the pattern, right? Whichever side you don't know, that's the letter you want to put here, and that's the angle that you must already know for the most part. Okay, two other things that you need to know here. One is that we can take this formula, I'm just going to do this in the middle of the screen, a squared equals b squared plus c squared minus 2bc, the cosine of a. And we can solve it for, get a highlighter here, solve it for the cosine of a. The reason we might want to do that is if you're looking for a side, you're looking for the side length a, and you know the angle a, this formula makes perfectly good sense. You plug in these two sides, the two sides here, the cosine of a, and then you just work out what this, you work out this computation, and you have your a squared. Then you have to take the square root. But if you know A, B, and C, the sides, the lengths of the sides, A, B, and C, and you don't know the angle, then you have a couple of choices. One is that you can plug the numbers in here for A, B, and C, and then turn around at that point and solve for cosine A, and then use inverse cosine to find the angle of A. Or you could solve this equation, this generic formula for cosine of A squared equals b squared plus c squared minus 2bc, can be thought of as a squared minus b squared minus c squared, if you subtract those quantities from both sides, equals negative 2bc, the cosine of a. Now I'm going to divide both sides by negative 2bc. And I get a squared minus b squared minus c squared over negative bc, negative 2bc, is the cosine of a. And that's one version of the formula. If I multiply the top and the bottom of this fraction by a negative 1, I'm going to get a positive 2bc down here, and I'm going to get a negative a squared, but a plus b squared plus c squared. So another version of this formula is b squared plus c squared minus a squared over 2bc equals, I'm running out of room, the cosine of a. Now, I think what I'm going to do, for the sake of record keeping here, is I'm going to move this formula, I'm going to tidy it up, and I'm going to move it to, maybe I'll put it in this space down here, and I'll clear this area as well. I wanted you to see where this version came from, but we don't need to keep the record. Some people write this formula as A equals the cosine inverse of b squared plus c squared minus a squared all over 2bc. It's kind of up to you. And in fact, I would argue you really don't need this version because you can always derive it from this version. I don't usually actually teach this version, but I see it enough. I see it on enough students' notes and index cards and things like that, that I thought it would be worth mentioning so that you all know, maybe you'll see it somewhere and you'll know where it came from. It is just a algebra performed on this version. Okay, the last thing I'm going to mention just now is that the other thing we can do with the law of cosines is the side, side, side situation. So let me highlight that. So I've got a highlighted version of each of these. Either side angle side or side, side, side. So this is the side angle side. If you know B and C and you don't know A, you know B and C, but you don't know A. You know B and C, and you also know the angle in between them. That's when the law of cosines comes into play. Or if you know B and C and you know the third side, then you can find the angle A. And that's actually the side, side, side situation. So this is kind of a precursor to that. I'm going to erase, let's see, what shall I do? I don't think we need most of this screen at this point for the side, side, side. I do want to leave, I'm going to leave both of these formulas down here. And maybe I'll leave this diagram, but I think I'll erase the rest. So if you have a triangle, let's just do a random triangle here, and you know the side, the lengths of the sides of this triangle, let's just say there, well, let's just call them A, B, and C for right now. And then using the law of cosines, using this formula right here, we can plug in A, B, and C. B and C can go here as well. Notice that we're plugging in a value for A, for side A, but not for angle A. If we know all three sides, side, 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 if we know all three sides, we can still use this formula, but now we're going to have to turn around and solve this for cosine of A. That's basically what we've done here. So that's an argument for writing this version of the formula down on your note card. Equally, if you have this version written down, you can still plug in A, B, and C here as well. Do the arithmetic, and then you've solved for cosine of A, and you can take the inverse. That's really all I think I want to do for the side, side, side version. We could do an example, but I mean, you know how to plug numbers into a formula, so maybe we'll do some more of these in class. Basically, in short, we can use the law of cosines for side, 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 or side, angle, side. We use the law of sines to solve the angle, side, angle, 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 side, and side, side, angle situations. Remember that the angle, the side, side, angle situation was the one with the, we call that the ambiguous case, where we have two potential solutions. We'll talk more about that in class. Now, the only thing we haven't talked about so far is the angle, angle, angle case. And this one doesn't have a formula for it. There's no way to solve a triangle if all you have for that triangle are all three angles. That ended up looking a lot more like an equilateral triangle than I really meant. Let's say you know this angle, and this angle. If I stretch this triangle, kind of like zooming into it, then you end up with another triangle with the same sizes of angles. This angle is the same size as this angle. This angle is the same size as this angle. And this one's the same size as this angle. But the side lengths are now different. If this had a length of, say, 1, this has been multiplied to have a different side length. If this had a side length of 3, then this one's been multiplied to have a different side length. And if this one had a side length of 4, this one's been multiplied to have a different side length. I'm just using a stretch factor of 2 here, but in fact, I could have stretched it by 3 times as much, or I could have shrunk it, and the same thing would apply. So there are actually an infinite number of triangles with these 3 angles. And so angle, angle, angle is not a situation we can solve. There are solutions, but there are an infinite number of solutions. Well, this is definitely a record. This is the longest video I've made for this class. But the good news is there are only two more subsections in this section. One is solving applied problems using the law of cosines, and the other is using Heron's formula to find the area of a triangle. The next one, solving applied problems, we've actually done the example in your textbook because it refers to that ship that sailed for 10 miles and then turned by 20 degrees, that problem. So the example in your textbook actually returns to that problem that was at the very beginning of the section and works through it. We've already done that. So I'm going to go ahead and skip the applied problems because that's a pretty good example of the kind of thing you might see. The next video, therefore, will be using Heron's formula to find the area of a triangle.